In this video, we will begin to talk about how we can deal with variability, and in particular, how to derive a summary estimate from variable data. First of all, let us talk about a very important word that we'll hear many times in the context of statistics, the word error. This word doesn't mean what it usually means in everyday communication. In the context of statistics, when we talk about error, we usually mean some form of variability and usually about unwanted variability that is otherwise known as noise. Error may also mean the difference from some assumed true value which is unknown to us. There can be systematic error, in which case it is also called bias. Error generally can mean uncertainty, lack of confidence. Variability is always associated with uncertainty. Error often means difference from a prediction. If we have a model to predict some values and we have some actual observed values, then the difference between these two is the prediction error or the residual error, whatever is left over after we're done predicting. The important thing here is that error does not mean mistake. Error means that our values are different from one another, different from what we want, or different from what we predict. To illustrate the ubiquity of error, when I was teaching statistics in an actual classroom, I would ask for 6 volunteer students in the beginning of the first class, and I would ask one of them to stand out, give a measuring tape to the others, and ask them to measure the height of the one brave volunteer. So each person would take the measuring tape, go on and measure the height of the one designated person, write their measurement on a piece of paper without announcing it, fold the paper so that it is not visible, and then the next person would do the same thing and on and on. This is the result from 2019. These are the actual writings of the 5 students who wrote down the height of one person, measured in class. So we get these 5 numbers that are supposed to be the height of the same person, measured at the same time, in the same place, with the same instrument. And you may be thinking that something is wrong, but this is actually what always happens. These are the numbers from the year before. So we have 5 values for the person A's height and 5 values for person B's height. This kind of variability, which is known as measurement error, is very common. In fact, it's always happened. Every year I've taught a class like this, and it's a very robust effect. If you think it's weird, you can ask 5 of your friends to do it and see it for yourself. So this is the reality. Reality is variability. And this raises an important question that needs a principled and justified answer. And the question is, what is the person's height? Of course, there is also the sobering consideration that in real life, if you wanted to measure someone's height, you would only measure it once, which is like having only one of these 5 numbers and not having the others. This prevents you from realizing that there is actually error associated with your measurement. But if you repeat it several times, then the error just shows up and you realize that no estimate is free from variability. So what are we supposed to answer when someone asks, what is this person's height? We need an answer obviously based on the observations, the data we have, and these are the data we have. How are we supposed to choose from these? What makes a good answer? We could use a statistical criterion, which is to minimize error in the sense of making the smaller error or the smaller distance from the actual true height, but we don't know what the true height is. So this is kind of a theoretical definition. In statistics, we can actually find out, the mathematicians can find out for us which procedure based on these data will give us answers that are as close as possible to the actual value using models. We're not going to do that, but it's good to have in mind that we need to understand what we mean by a good answer before we can begin to think about giving one. Let us now see some common ways to produce summary answers from a set of data like this. The simplest approach is democracy. Let them vote. So each value gets as many votes as the times it appears in the data set. In this case, we find the value that occurs most often. That's the value 162 centimeters. And this is called the mode, the value that happens most often in the data set. Unfortunately, there is one complication with the mode, and that's that there may not be one value that's seen most often. For example, the measurements from 2019 for this same class exercise were the numbers you saw before, which have 172 twice and 171 twice. In this case, there is no mode. Another approach is to first sort the observations from smallest to largest. So these are the numbers we obtained, and we just put them in order. So this is the smallest value, progressively going on to the largest value. And then pick the one in the middle, and that is called the median. Finally, the third approach, one that you are certainly familiar with, is to allow all values to influence our answer in the same way. So if we have these 5 observations, what we can do is to add them up and divide by how many they are. And this is the mean, and it's symbolized with this Greek letter mu. You already know how to do this. The issue that arises with the mean is what happens if some values are not as good as other values. I'm going to give you an example of what I mean with that. So our original observations, these numbers, have produced the indices we have already discussed: the mode, the median, and the mean. And as you see, these 3 possible answers are very close to each other. But now let us imagine that one of the 5 students actually made a mistake, the tape slipped, and instead of reporting this value, we got this one. But we don't know that a mistake was made. All we have are these 5 numbers to work with. So if we just calculate the same indices, the mode is again 162, the median is again 162, the mean is now almost 163. That's quite a bit higher than the previous one. So what happened with the mean is it was most affected by the occurrence of a problem in the measurement process. And if we weren't aware of this mistake and we're just using the numbers as if everything was fine, then this would result in a biased estimate, a misestimation of the height of this person using the mean. Another example of a problem that can arise with the mean, let's imagine that you have applied for a summer job, and then you visited the place that you have applied to, and you found 5 people working there, and you asked them how much they earn. You're interested to know what your salary may be as you consider the possibility of working there. So let's assume you asked everyone you saw there, and they all answered truthfully, and you got these answers. These are 5 numbers from 5 people. The mode for these numbers is not defined because no value appears twice. The median is 160. and the mean is 222 crowns per hour. How much would you expect to be paid based on these data? Well, if you take up the job, you will realize that one of the 5 people that you asked actually was the boss. So this number is a different kind of number from all of these. They're not all measuring the same thing, the hourly wage of an employee, like the one that you would be. So by allowing the mean to be influenced equally by all the answers, you have produced an estimate of how much you would be paid using the procedure of the mean that is actually not a good one. So the mean, which generally happens to have good properties and we tend to use it all the time for very good reason, also comes with some assumptions and some issues we need to be aware of. All these things that we have talked about are called indices of central tendency because they are estimates of where the center of our observations might be, like the center being a value that would be reasonable to consider as the answer based on all of the observations taken together. The mode that we saw first can be used even with nominal level variables, so nominal scales of measurement. Can be used with categorical variables because it only requires you to count the values. And you can always count how many labels you have in a categorical variable. One difficulty with the mode is that it may not be defined if there is not one value that is more frequent than all the others. But otherwise, the mode can be very useful. The second index of central tendency is the median. The median can be used for ordinal level data and above. As long as you can rank your data, you can produce a median. And the median, like the mode, is a value from the data set. Now, actually, for the median, that's only true if there is an odd number of measurements, in which case the middle one exists. If there is an even number, you have to do something about the 2 middle ones, and that's easier to decide when they're numbers than when they're levels of an ordinal variable. A very desirable property of the median is that it's generally stable and it's not easily fooled by having values that are far off due to problems. Values that are distant from the others are called outliers, as they lie outside the distribution of the rest. And the third index of central tendency that we saw is the mean. The mean requires numbers to be calculated on, so it can only be used for interval or ratio level data. That is, only with numeric or quantitative variables. The mean produces a value that may not actually appear in the data. So you can have a mean value of children per family be 2.5, although no family ever has 2.5 children. And the mean has some difficulties in the sense that it depends on assumptions for where the data points come from and how they are distributed. So what are we supposed to choose then? What is the best answer about this person's height or about situations when we have some set of data and need one summary estimate from them? What is the most appropriate statistic for the set? Unfortunately, different cases require different answers. So this is why we need to understand the properties and assumptions of the different indices so we can choose wisely which one to use in each case. For numeric, that is quantitative variables, we usually use the mean, and the mean is known to minimize the error in the long term. That is, if you always use the mean to produce these kind of answers, in the long run, this will lead you to make the least error, that is, to be least distant from the right answers. However, the mean needs to be used with caution.